Good afternoon, everybody. It's my pleasure to introduce today's house speaker, Dr. Adam Sobel from Columbia University. Adam is a very prominent scientist in our field, in the field of tropical meteorology and others. And he got his PhD in 1998 from MIT. And ended up as an assistant professor at Columbia University around the 2000s, and grew to the ranks to full professor, and became a professor in 2010. And he has more than 100 peer-reviewed publications, and he is a recipient of multiple prestigious awards, including one from IMS, award. So I think we're very fortunate to have him here, and let's meet Dr. Sobel.
Thank you, Murat. Thanks everyone for coming and for having me here. It's always a pleasure to be at Stony Brook. It's been a few years since the last time I came. So I guess I advertised a title that was slightly different than what I'm showing now, but the material is about 60% the same as what I thought I would say when Murat and I first discussed this months ago, but I hope it's still interesting. I'm going to talk about some work we've been doing on tropical cyclones for some years, and then more recently, a few years ago, we started doing some work on tornadoes and hail, actually, although I won't talk about hail today, I don't think. And the way this happened was that hurricanes and tornadoes, of course, are completely different meteorologically. But when you start to ask how each of them is related to the climate, there are some methods we have been using that worked reasonably well for one that we thought would work for the other two. And so we got into the tornado problem, or severe convection over land problem, for methodological reasons. We thought there was a gap in the literature last time I came. So I guess I advertised a title that was slightly different than what I'm showing now, but the material is about 60% the same as what I thought I would say when Murat and I first discussed this months ago, but I hope it's still interesting. I'm going to talk about some work we've been doing on tropical cyclones for some years, and then more recently, a few years ago, we started doing some work on tornadoes and hail, actually, although I won't talk about hail today, I don't think. And the way this happened was that hurricanes and tornadoes, of course, are completely different meteorologically. But when you start to ask how each of them is related to the climate, there are some methods we have been using that worked reasonably well for one that we thought would work for the other two. And so we got into the tornado problem, or severe convection over land problem, for methodological reasons. We thought there was a gap in the literature that we could fill by using some methods that we borrowed from tropical cyclone studies, which turned out to be in some things that the tornado people were sort of doing already, because they're smart people too, but we had some, our own perspective on it. So anyway, this is bits from a few pieces of work done over a few years with a few colleagues. Michael Tippett especially, the key person in all of this, because a lot of it is statistical methods, and he's really our statistics expert who's developed a lot of this. Susana Camargo, I've been working on hurricanes with her for a lot of years. John Allen is a postdoc who's doing tornado and hail stuff with us. And then I'll show some bits and pieces from collaborations with a few people from other institutions than Columbia. The top line is all people from Columbia, but also some a result or two from Kerry Emanuel, and then from GFDL, Ming Zhao, and Gabe Becky. So we're interested broadly in the probability of a given extreme event. So let's say we're somewhere on the Earth, Long Island, and we ask, what's the chance of something happening? Some kind of severe weather event that has short time and space scales, like a hurricane or a tornado. And we want to know not just what's that probability now, but how that probability will change as a function of climate. And the climate could be varying for natural reasons, like an El Nino, or it could be varying due to human influence. That's the problem broadly that we're interested in. And now I'm going to talk about that, as I just said, for both hurricanes and tornadoes. And I'm going to argue, just to repeat myself, that although they don't have much to do with each other at the level of physics, that there's some common methodologies we can use to think about both of these. And there's some reasons why it might be useful to use those methods for both of these problems. They have some other features in common at the level of methodology. So just some differences. This is probably not something that needs to be said for this audience, but let's just get it on the same page. A hurricane's, of course, a much bigger thing. Even though it's a small storm, it's still much bigger than a tornado and lasts a much longer time. A hurricane lasts a week or something, a few days or a week or more, and a tornado lasts, minutes to maybe hours at the outside. Hurricanes form over the ocean almost always. Tornadoes mostly over land, unless they're related to a hurricane. This is a little more subtle, but hurricane is often said to be in quasi-equilibrium with its environment, meaning it's taking energy out of the ocean, it's moving into the atmosphere, and it's kind of in some kind of a rough statistical steady state, even though it's evolving in time, but the evolution is slow compared to the internal cycling. So they're in quasi-equilibrium with their environment. Tornado is not. Tornado is something that, you have a very powerful thunderstorm, it just spins off this vortex that just, dies when it runs out of steam. So that's some differences, but some similarities. And these, again, are really methodological similarities. So the previous thing was physical differences. The similarities are not physical, but for both of them, we have some data, right? We have some historical records, and they're good enough to do some things. I mean, we often talk about the data problem when we're talking about climate and severe events, but we do have some data. But they're good enough for some purposes, but they're, in both cases, problematic for looking at the climate change question, and I'll show you briefly some evidence of that. In both cases, we don't have really good theories that tell us the answer to what we want to know, which is change the climate, how does the probability of the event change? We don't have really a complete theory, or in case of tornadoes, we don't even have an incomplete theory. We don't have anything, really, to tell us the answer to that. So we could use models, but global climate models, ideally, you'd have a global model, and you can just simulate everything. Maybe Murat's getting to the point he can almost do this. But even those models don't have tornadoes yet, I don't think. You need to be down in meters or something, right? So you need a global model if you want to simulate the climate, but you need a very high-resolution model if you want to simulate these events, especially for severe convection over land. So the brute force approach, doesn't work so well, although it's starting to get there for tropical cyclones, but it's still off limits for tornadoes. So just to say a little bit more, so this is all to motivate the approaches I'm going to talk about, which broadly you could think of as statistical downscaling. But that's probably the last time I'll use that word, but that's really what the methods I'm describing today are. Just to say a little bit more about the data, this is from a paper by Gabe Becky and Tom Newson, looking at trends in Atlantic hurricanes. Atlantic's the basin where they're the best, and this is showing since 1880, and they're going up and down, and there's some upward trend. But then when you take account of the fact that you might have missed some back here because there weren't enough ships to see all the storms over the ocean, then you make an estimate of what that might have been, and you put those in, then the early time comes up, and you have a flat line and no trend. That's just giving a sense of what some of the data issues are. But you can also see just huge low-frequency variability in this that makes it, any trend you would get from a data record this short is going to be hard to have a lot of faith in. So that's just saying that looking at the climate signal in these extreme events due to just from observations is tough. So, okay, observations are tough, so what about theory? What do we think theory should tell us about how tropical cyclones are related to climate? Well, we do have a theory for hurricane intensity, and I guess I took out the slide where I explained the details of it, but basically so-called potential intensity theory, which is developed originally by Kerry Emanuel and has been contributed to by a few others, is a theory that describes the hurricane as a heat engine. In the simplest description, it's a Carnot cycle, and that tells you the maximum intensity the hurricane can reach given some key environmental conditions, the sea surface temperature and the large-scale atmospheric sounding over it up into the lower stratosphere, then you know what the maximum intensity a hurricane can get to. That's the potential intensity theory, and it's, I think, stood up pretty well to many challenges in the test of time. So we do have some, despite the issues with it, we have some fundamental understanding of what controls the intensity of a tropical cyclone. Now, the theory only tells us about the maximum intensity. So most hurricanes don't reach the maximum, but they're somewhere in between. And this is a nice paper by Kerry Emanuel from 15 years ago that shows the cumulative frequency distribution of the actual intensity of cyclones divided by their potential intensity. So that's typically going to be a number between 0 and 1. So that's on the x-axis. And then the cumulative frequency is here. So that's the derivative of the PDF, the probability density function. So, and I don't actually remember what the difference is between the 4 different plots now. But this is all for, some are Atlantic, some are Western North Pacific. And yeah, and the one is with putting in the translational velocity of the storm, and one is not, but it doesn't really make much difference. And this is all for storms that, the peak intensities of storms that don't, but not when they're hitting land. You have to avoid times when they're hitting land or moving quickly over areas of colder water, because then the potential intensity is changing too fast and the storm is not in equilibrium, right? In other words, if you have a very strong storm that suddenly moves over cold water or land, then it'll look much higher. The actual intensity will be higher than the potential intensity by a lot, but it's because it hasn't equilibrated yet. So he takes those out of the data. And then what's left is this CDF is a line, which means the probability density function would be flat, because that's the derivative of this, between about 0.4 and 1, which means that between some lower bound, which turns out to be roughly hurricane intensity, and the potential intensity, a storm has an equal probability of reaching any intensity in that range. In other words, the potential intensity tells you the maximum. The actual intensity is like a random number between the lower bound and that with some uniform probability. So if you assume that's an empirical result, we don't know why this should be the case. And it requires the taking out the storms that are moving over cold water, like I said. But if you assume this to be true, then you do have a theory for the actual intensity of cyclones, because you know the PI, the potential intensity, and the actual intensity on average is going to be proportional to that. Less than, but proportional if you assume the uniform distribution. So that's a long argument. But this is just to say we did a test of this a few years ago, and it kind of works on interannual variability. So what this is a calculation. Alison Wing, who was an undergraduate at the time, actually she went and got a PhD and has come back and is now a postdoc with us. This is work she did when she was an undergrad. And this is showing for the North Atlantic and the Western North Pacific, we took all the storms in a given year, computed their maximum intensities, normalized by potential intensity, and computed their maximum intensities and averaged that for each year. So that's annually varying sort of average peak intensity of cyclones, and varies because of El Nino and other things. And this is the actual intensity. This is the potential intensity computed on the tracks where the storms were. You have to do that. You have to know where the storms are. And there's a good correlation between these. And this is the scatter plots of one versus the other. So it's just saying, I won't explain what this upper curve is. Doesn't matter for now. It's just saying that potential intensity theory, the correlation is by no means perfect, but it's statistically significant and not bad. So potential intensity theory explains some of the interannual variability in actual storm intensity. So all that's just a long way of saying we do know something about the intensity of storms if we know something about the environment. If we have a climate model that predicts a large-scale environment, then we can tell us something about how storm intensity should change. But if we want to know about the frequency, potential intensity theory only tells us what the intensity could be given the storm is there, but it doesn't tell us whether the storm is there in the first place. And so we have no theory for that. We know a lot about tropical cyclogenesis, but we don't have anything that tells us what the absolute rate should be. So in other words, why do we have 90 cyclones on the Earth per year, plus or minus 10, and not 200 or 300 or 20? We don't know that. So if we want to predict how that number changes with climate, we can't use theory because we just don't have it. So one thing that's become popular in this field is so-called empirical genesis indices for tropical cyclogenesis. The first one was developed by Bill Gray, I think around the 70s or early 80s. I can't remember the exact reference. But the idea is you think you know what variables are important for genesis, sea surface temperature, wind shear, and those kind of things. And you try to find a function of those variables that gives you some prediction of genesis. So this is not Gray's. This was one that was developed by Carey Manuel and Dave Nolan a few years ago. And then we wrote some papers using it where through a statistical procedure that's not actually described that well in the literature, but they come up with this number. So this is these are the variables. Gray had 6. We got it. Emmanuel got it down to 4. We think 4 is actually the right number. So one is absolute vorticity at 850 hectopascals. That brings in the Coriolis parameter. You know, the hurricanes can't form on the equator, so we have that. Some power. These powers come from some statistical fitting procedure. That's, you know, I'm not going to go into, but positively related to absolute vorticity, including Coriolis. Relative humidity, potential intensity is where the sea surface temperature comes in. So that's something that predicts the intensity, but it's also one of 4 predictors for the probability of genesis. And then vertical shear appears with a negative exponent, so cyclones don't like vertical shear. So the claim is that this number, you can calculate this from the environmental state, and this number should be proportional to the probability of tropical cyclogenesis. So it's similar to potential intensity theory in that you have some environmental variables that tell you something about the cyclone, but here we're getting genesis rather than intensity, and this is not based directly, I mean, it's not a purely, potential intensity theory comes from a physical model. It comes from a physical theory. This is really an empirically derived thing. You need to use the genesis observations to determine this function. But this is just to show that you can then use it to predict something you didn't know. So this function was derived from the climatology, just looking at all the data at once, one annually varying climatology for the Earth, and looking at the spatial distribution and seasonal distribution, but not using year-to-year variability to derive this. So then you can test it to see if you can predict interannual variability. So this is the paper we did a few years ago where we took this index and calculated it for El Nino years and La Nina years and then subtracted them. So this is the difference. This is El Nino minus La Nina. And you can see this index predicts more storms in the East Pacific and in the Central Pacific in an El Nino year, and fewer in the far Western Pacific, fewer in the Atlantic. And this is the observation, the observed track density. It's not actually genesis. Genesis looks similar but is noisier. This is the track. There's more points if you use track density. So you can see there's more here and fewer here. So it's just to say this index, again, the information about ENSO wasn't used in deriving it, so this is a non-trivial prediction. So it's just to say that these indices, although they're empirical, they do have some predictive power, right? We can predict something that we didn't use to train it. So that was sort of our first time we got interested in these indices, when we convinced ourselves that they could do something useful. So we developed our own a few years ago. There were some things about the Emmanuel Nolan index that we thought could be improved, and you can improve it a little bit, not that much. But the main thing that's different with this one is that the derivation is totally objective, and you can reproduce it. So again, what this is you take all the observations of tropical cyclones. You have a map of where genesis occurred throughout history, just putting all the data together. So you get a field of the probability of genesis derived from the climatology, and then you have these environmental fields that you get from your reanalysis or your favorite data set, and you do a fit. And this fit is called Poisson regression. That's a method. It's a routine in MATLAB or whatever. And then that's how we do it. And we tried many different environmental variables. These are similar to the ones Emmanuel used. They're not exactly the same. In this case, instead of potential intensity, we used relative SST, which is simpler. We'll go back to PI later, but relative SST is the sea surface temperature minus the tropical mean. And that's a good proxy for potential intensity, actually. But tropical cyclones don't just like warm water. They like the warmest water on the planet, whatever that is. And so this is a measure of that. So anyway, we do this Poisson regression. We try other variables, and we pick the 4 that work the best, and it turns out to be these 4. And you want a parsimonious index. It turns out if you use less than 4, you don't get as good results. If you use more than 4, you might make it a little better, but you run the risk of overfitting. So this is for.
What is the time scale implied here? Is there one?
There's no time scale implied. In other words, well, what do you mean by time scale?
Can I use it to find the daily probability of typing?
Well, okay, so these are the issues with that. So again, the simplest thing is just to say how it's derived. It's derived using all the data together. So it's
on a seasonal basis?
On a climatological basis. So yes, seasonal, yes. So what you have is take all the cyclogenesis events and make a dot on the map for each one, and then you have a density when you add up all the years and divide by the number of years. Then you make one map like that for each month. So you have 12 maps, and then you have these variables, climatologies of 12 maps of these, and so you have 12 maps times however many points on your map, and you do a fit Poisson regression, and it's exponential because that's what Poisson statistics gives you. And so then if you want to use it for daily, it probably has some information. The trouble with daily is, I mean, first of all, it's not going to be, the chances of genesis are always low. So it's never going to give you tremendous skill. It could work well daily. We haven't really tried it. Part of the subtlety is that often you already have a storm forming that influences, I mean, these fields, because these are climatologies, there's no storms in this field. It's really the environment. But once you have something forming, you have to somehow account for that. And so you would want to rederive an index from daily data if you want to do it. But then the problem then is that your genesis data is much, much noisier because it's incredibly rare on a daily time scale. So those are the trade-offs with doing this kind of calculation. But so we think it's most useful on probably longer than daily. Maybe intraseasonal. We wrote a paper about MJO, and we showed it has some skill for that. But you get down to daily, you might be better doing other things to predict genesis. Anyway, so this is an index that we derived. And because it's an objective derivation, you can, if you decide you have different predictors, or some new data set comes out, you can just recompute it. And the coefficients will change. So this is exponential instead of powers, but it's similar. You have some coefficients and you have your variables. And I'll talk about this in a minute, why this minimum is there. Yeah. So that's one thing we learned from this, is that we get the best fit not from using absolute vorticity itself, but for using absolute vorticity up to a maximum value, which is about the value at 20 degrees. That's what this is 3.7 in units, which I don't remember, but this corresponds to the Coriolis parameter about 20 degrees. What we find is that we get the best fit when we assume that the probability of genesis increases with latitude up to about 20 degrees, or up to about that that absolute vorticity, and then it doesn't help after that. In fact, it becomes anti-correlated after that, which is because actually Coriolis parameter is oppositely correlated to SST. The problem is that all these predictors are correlated with each other. So this is something we learned, that you need it tells us, we actually think it's telling us something physical. You need some rotation to have the initial development of a cyclone, but past some point, more doesn't necessarily help you. So that's...
Why you need relative resistance and not actual resistance?
Very good. Good question. In today's climate, if you stay in the same mean climate all the time, it wouldn't matter which you use, because they're going to be very similar, because the mean wouldn't be changing. But if you just add, so you might, if you think absolute SST is what matters. Well, actually, I'm going to come back to that in a couple slides. Yes, good question. Let's come back to that. I have a couple slides about that.
Is the mean tropic SST
Tropic.
the average from like 20 to 20 degrees?
I can't remember if you use 20 or 25 or what, but something like that, yes. So you have to, this is exactly Murat's question. You have to be really careful using this kind of index for climate change. They're derived from the climatology. So you're tuning something to some range of variability, and that variability comes from the annual cycle and the spatial structure in the present climate. Okay? But now you do global warming, you're out of your sample, and you don't know what's going to be the same. And so, for example, it's been known for a long time, this is from a Palmain 1948 paper, that cyclones like warm water only form above 26 or 27 in today's climate. So you might use sea surface temperature as a predictor. And that's what Bill Gray did in his 79 paper. That's the actual year it came out. He put in, instead of putting tropical mean, he basically put, SST minus 26.5 or something. as long as it's greater than 0. That was his predictor. So we think you shouldn't use an absolute number. You should use the tropical mean. And the reason is that we think this threshold should change as the climate does. Basically, it's like a convective stability argument. If you think that tropical cyclones will always form at 26, 27 degrees Celsius, then if the whole planet gets 2 or 3 degrees warmer, the area above that temperature will get much larger. You should have many more tropical cyclones and forming at higher latitudes. And we actually don't think that's going to happen. That's not what the high-resolution models do. That's actually the best models today that simulate this. What happens is the atmosphere warms up too. So the tropical cyclone is feeding off the ocean atmosphere temperature difference. But the atmosphere warms up with the tropical mean. So now you have to reach a higher threshold to form a storm. And this is a simple calculation we did to try to show that. But this happens in very complex models as well. But this is our attempt to explain it. This is a single column model run 2 different ways. So, and here we're running our single column model to radiative convective equilibrium. So just simple SST, let the convection and radiation come into equilibrium. You get an atmosphere that's roughly moist adiabatic in equilibrium with the SST. And then you compute the potential intensity, the Emmanuel potential intensity. So what's the peak intensity of a hurricane in meters per second? And then you change the SST. And that's this curve here. You get a very slow increase of intensity. So I'm talking about intensity here, but we'll come back to frequency in a minute. Now, in this calculation, you raise the SST, but you don't let the atmosphere adjust. So that's like relative SST. If you think of changing the SST just in one patch, then if I raise the SST, the atmosphere is still going to be on a moist adiabat that feels the whole tropical mean, because the atmosphere in the tropics has very small temperature gradients. So it has to be convectively adjusted to the whole tropic. So if I change the SST just locally, then and I have to allow the large-scale circulation to come into equilibrium with it. That's something we call weak temperature gradient approximation. That's what this is. That's how we did these calculations. And I won't explain the details of it too much. I think the students got a couple of papers. I don't know if you guys read them or not. But this is where you just change the SST of the surface and don't change the free troposphere. So it's like relative SST. And there's an implied large-scale circulation. The PI increases much, much faster. So we think that this is what's explaining the variations of cyclone intensity in the present climate as a function of space and season. Whereas this is what you would get, something like this, if you were to just warm the whole planet uniformly, keeping the structure the same, right? So you still get some change, but it's much smaller. So this is just to say that if your index is trying to capture that variability, it's relative SST that's what you want. And it's a very good proxy for PI. It has a strong relation to PI. This has a very weak relation to PI. This is just to show, after we did this, Carrie Emanuel and I did another study where we did these calculations the same way, but now with a coupled model. This was done by a postdoc a few years ago, Hamish Ramsey. This was done with fixed sea surface temperature. Carrie redid them with the same single column model. Both of these were done with Carrie Emanuel's single column model, particular convective scheme and radiative scheme. Doesn't really matter. These were done the same way, except with a slab ocean. So the ocean changes temperature. So instead of just changing the SST, we change things that control it. We change the solar radiation or the CO2 or the surface wind speed, which affects the surface fluxes. Or you just do fixed SST. That's the dark blue. And these are, again, relative SST calculations, so weak temperature gradient calculations. And the point here, actually, is that, so now, this is just the relative SST as an output of the calculation, because we're predicting the ocean temperature. But they're holding the atmosphere temperature the same still, above the boundary layer. Actually, that's a technicality. And actually, all these curves, there's 4 different ways you can change the sea surface temperature. And they don't have to give the same answer, but they sort of almost do for relative SST in terms of what the potential intensity is. And this is where we calculate the Genesis potential index. This is actually the Emmanuel Nolan Genesis potential index as a function of relative SST. And Carrie's point in doing these calculations was that you can get different answers depending how you change the SST. And so for surface wind speed in particular, gives you a stronger response. If you warm up the SST by reducing the winds, you get a stronger change in potential intensity than if you do it by solar radiation, for example, which is the light blue, or the magenta thing here. But they're pretty close, actually. So relative SST doesn't capture all the coupled dynamics, but it captures some of it. Of course, it doesn't capture this global mean change. If you just warm the whole climate, you do get some overall increase in PI, and relative SST won't capture that at all. Just imagine you add 2 degrees to the temperature everywhere, and the storms all got a little more intense. Relative SST hasn't changed, so obviously it's missing something. But that's, yeah.
In your single column model, how did you do the relative SST? You run 2 simulations?
No. It's weak temperature gradient. So we have so here's temperature as a function of height, right? And we specify the atmospheric sounding, but we change the SST. Okay. So the boundary layer will adjust, and this one will be very unstable, have a lot of CAPE. This one will be very stable. And what happens is then, if you generate, whatever heating you generate is balanced by large-scale vertical motion. So you have, your omega field times some static stability always equals your heating in the troposphere. So that's how you, and this affects the moisture convergence and stuff. So you have you can have precipitation and evaporation not being equal, for example. But this one, you can see this one will have some kind of inversion and will be very stable, and you will have dry conditions. This one will be very unstable and have a lot of convection. So this one will have a high PI. This one will have a low PI. But that's what we did in this case. In the other case, we're changing the sunlight shining on here or changing the ocean heat transport or something. But the fact that this temperature is fixed represents that we're just thinking about a little patch of ocean, and the atmosphere in communication with a large atmosphere. So this temperature is constrained by dynamics to be similar to. Is that clear?
Yeah.
Okay.
So it's specified tropospheric temperature.
Correct. Yep. That's how we define relative. Yeah. Okay. But this is just to point out that you do get different answers for some things. So the coupled system dynamic. There's an argument of whether you should use any kind of SST as a proxy for cyclones, and this is so for relative SST works okay for some things. This is though in those same set of simulations, this is the precipitation, and it's just to show that you get similar answers for all the forcings except surface wind speed. This is interesting. If you increase relative SST by slowing down the winds, you actually get less rain. If I increase the SST, I'm arguing here I should get more rain because I'm unstable. I have lots of CAPE. I could draw my CAPE and I would get lots of convection in the tropical atmosphere. But if I do it by decreasing wind speed, because of the way it interacts with the ocean and atmosphere interact, it's a long story that I don't want to get into because I want to talk about hurricanes and tornadoes. But you actually get less rain instead of more. So there's some coupled dynamics that are, just to be fair. Kerry and I are co-authors on this paper, and his takeaway message from it was that coupling changes everything, and my takeaway was that it actually doesn't change that much, even though we agreed on what the paper actually says. But I just want to show this slide to be fair that it does change something. Okay, but now to move forward. So we have these genesis indices, but how can we show that they work for climate change, given that they're tuned on the present climate? We have some physical ideas. I've given you some physical arguments why you shouldn't use absolute SST, for example. We know some things that we can do wrong for climate change, but how do we know if we're doing it right? Well, the exciting thing now in the last decade or so is that we have these high-resolution models, which global models that not quite as high as Murat's, but on a global basis, sort of 10, 20, 50 kilometer grid spacing models that we can now afford to run for many years, at least atmospheric models, which is starting to happen coupled now. And 10 to 50 kilometers, not so great that you have perfect hurricanes, but the hurricanes can look pretty good. This is from a Japanese simulation. They were one of the first to do this. So you can see this nice kind of cyclones there. So we can do climate change and cyclones with these. And what you find in these models as you make the climate warmer is that they predict there will be actually fewer cyclones than there are at present. It's the opposite of what people used to think. People used to think cyclones like warm water, so we make the water warmer, we'll get more cyclones. These models, for the most part, say the opposite. And we're trying to understand that result, and we're going to try to use our indices to understand it. So there was an intercomparison project a few years ago. A bunch of groups running these models did the same experiments and compared them. These are climatological track densities, annual mean, how many storms there are, plotted as a density function for all these different models. And some of them, this is the observations. Some of them look better than others. Some of them look pretty bad. Each model is tracking the storms in a different way in this plot, which I don't want to explain. But I'll just argue that after a lot of study, it's pretty clear that this model is the best of this bunch. The GFDL HIRAM model looks a lot like the observations, and their way of tracking the storms is pretty faithful to how it's done in the real world. So this is the one we're going to focus on for the moment here. And so what we did was we used this model as a test bed to both test our genesis index methodology. In other words, we're doing a perfect model experiment where we take this model as truth and see whether our genesis index approach can predict what it does as the climate changes. And also, in the process of doing that, this is a good way of interrogating the data, so you learn something about what the actual reasons are for the decrease in cyclone frequency. So what we're going to do is we're going to derive our genesis index using Poisson regression again, but not from the observations, but from the model itself, from the model's own storms and its environment. So we have this objective procedure, Poisson regression. We can any data we have, any data set where we have storms and environment, we can do this. So we do this from the model itself, and then we warm the climate, don't change the index, and see, but just recalculate it from the new warmer climate, and then see what it predicts about how many cyclones would appear. So this is taking the GFDL model as if it was perfect and testing whether our index approach works. So I'm just going to go straight to the main result here, rather than showing you a lot of details. What's happened here is these are a bunch of different simulations. So I didn't explain. This is actually not results from the Cliver working group. These are results from the HIRAM model simulated over, it's an atmospheric model, so the climate is warmed by increasing CO2, but also increasing the SST, because it's not a coupled model. And the SST warming for a sort of doubled CO2 experiment is taken from a bunch of different climate models, global climate models from CMIP, if I'm not mistaken. That's what this represents. I know. It's a bunch of different realizations at any rate on this axis. And what's shown here is the number of storms, the change percentage-wise in the average number of storms per year on the globe, tropical cyclones. In the model is the white bars. So you can see that in all these different climate change scenarios, the number of storms is decreasing by something like 20%. And this is where we took our index and calculated what it should do. So we derived the index from the model in the present climate, then take the future model's climate and compute the index, not looking at the storms in the future model. We're trying to predict that. And we get the wrong answer. We find that it should increase. But then, thinking about some dynamical arguments about what we think should be causing this decrease, we realized that our predictor, our humidity predictor, is column relative humidity, which is the total column water vapor divided by what it would be at saturation. And we had the idea to replace that with saturation deficit, which is the difference, right? So in other words, what did I do with my, our relative humidity is Q divided by Q star, right? And saturation deficit, can't really erase, saturation deficit, which is, let's call it S, is Q star minus Q. So one is a ratio and one is a difference. But what climate models tend to predict is that this stays approximately constant as the climate warms, but this is going up, so that means this will increase, right? And in the present climate, if you look at maps of this and maps of this, they look almost identical. But as the climate warms, systematically this one goes up and this one doesn't. So when we replace our humidity predictor, instead of using this, we use this, but column integrated. It doesn't change the present climate results at all, but it gives us the right answer now in the future climate. So we now think that this genesis, we think this is telling us something. We think it, first of all, it means the index works if you have the right predictors, and that the saturation deficit should be important. And there are some thermodynamic arguments why that should be, which I won't go into now. If people have questions, I can go into it. But we think there are some thermodynamic reasons why this absolute difference, the amount of humidity you have to add to reach saturation, should matter. And so that's indicated by these results. This is what we think it's telling us. I already said that. I also said that too. Yeah. The thermodynamic reason is that basically this is the absolute entropy, proportional to the absolute entropy that the storm has to get from surface fluxes. And so as this number gets larger, the the storm has to work harder to pull that entropy out of the ocean. All right, so I'm going to say a few words about tornadoes now. I think I have enough time to do that since I promised to do so. This is the definition of a tornado. Skip that. They form over land. You guys probably know this. This is the observed total number of tornadoes in the, between 1979 and 2010, mostly in the central United States. This is just showing you, as we did for hurricanes, that the data have problems. So this is the total number of storms in the United States. We don't really have good global data sets of tornadoes. We have to focus on the U.S. These are we rate tornadoes intensity on the Fujita scale. F5 is the highest. So these are all tornadoes F2 and higher, roughly constant numbers. This is F1 and higher. There's sort of a trend at the beginning, and then it sort of flattens out and oscillates. This is all tornadoes, including F0s. You can see it going up and up and up very fast. Looks like a huge climate change, right? Nobody believes this. This is widely understood to be an artifact of changing observing practices. More storm chasers out there seeing the storms. And so you can try to correct for it a variety of ways. And you could only the most intense ones, and maybe the problem is reduced. But the bottom line is, if you want to include all the storms, you have a problem, because you can't absolutely correct this. The data is only what it is. You can't go back in time and re-observe what was there. In fact, you never really observe a tornado. I mean, these are all, the intensities are estimated from damage reports on the ground afterwards, which is another problem. How you do that changes over time. And you can't really use models. I mean, you can model the sort of big convective systems that produce tornadoes, and this is from a paper by Mark Stalinga. There's a couple different models at what was fairly recent radar images, synthetic radar images. Well, this is a real radar image. This is a synthetic one from some simulation of the storm at cloud resolving resolution. But so you can get sort of the big picture, but the tornadoes are much too small even to see on this scale. So you can't do it with brute force. Even more difficult than for hurricanes. But just like with hurricanes, we can relate them in some semi-empirical way to the environmental ingredients. And so typically, if you read the literature on tornadoes, and the best work really on relating tornadoes to climate is a lot of the best work, and certainly all the best work until recently, when he's got some more competition now. But Harold Brooks and his co-authors have done a lot of good work on this. And it's quite clear that the two essential ingredients for severe convective, the kind of storms that produce tornadoes, and it's similar for hail, by the way, is you need a lot of instability, convective available potential energy, for example. You need the ability to form very strong updrafts, so large partial buoyancy rising from the boundary layer. And you need vertical wind shear. That's important for the organization of the storms on the mesoscale. To get the strong organization you need to produce tornadoes. So that, or instead of shear, people like this parameter called storm relative helicity, which is not exactly the vertical wind shear, but it's similar to it. So those are, if you know those two things, then you have some idea whether you have a chance of forming a tornadic thunderstorm, especially supercells. And an interesting thing is that over the US plains, these two parameters change oppositely with global warming. The models tend to predict that the jet stream moves a little bit away and moves a little bit north, and so that reduces the wind shear over the plains. But at the same time, the warming itself, the increase of humidity and temperature in the boundary layer gives you a larger cape. The models pretty much agree on that. But these are changing the opposite way, so will we have more tornadoes or fewer? Because the shear wants to make more as it decreases, but other way around. The shear decreasing wants to make fewer. Tornado, unlike a hurricane, likes vertical shear. So as the shear reduces, there should be fewer, but as the cape increases, there should be more, but which wins? That's the problem we have. And I'm not going to solve it today, but I'll just describe some of the issues. So this is the index we came up with for tornadoes. We did exactly the same thing. Take all the tornado data, make a climatology, take a bunch of parameters, and do our Poisson regression. Again, without going into the details, we tried a lot of other parameters and try to come up with the most model that explains the most variance with the least, fewest parameters, most parsimonious. And we come up with a two-parameter model. Storm relative helicity between 0 and 3 kilometers. It's like vertical wind shear. And instead of CAPE, we use convective precipitation. This was done using the North American Regional Reanalysis, which has a convective precipitation. That's a function, of course, of the model. This is a simulation data set. This is a function of the model convective scheme that was used for the assimilation. But that's fine as long as, as long as you have that model to do prediction with, it's a fair parameter to use. So again, we just take all the data. We don't use any should say no interannually varying data. It does vary annually. We have 12 seasonal maps and of all the parameters and the tornadoes themselves. So just climatology. Everything's on a 1 by 1 degree grid. This is the data on tornadoes and hail. We've done it for hail also, although I don't think I'll show that. We include the F-zeros, and that'll be important. We showed you the F-zeros have a spurious trend. But now we don't care that much about the trends because we're just averaging all the data together. We're not using the time variability. We're just taking the climatology, and we believe the climatology, which again is this picture. This is what we're fitting. This and its annual cycle. This, we think the trend, the spurious trend shouldn't matter that much for this because we're just averaging all the years together. We don't worry about whether the observing practice has changed because we're not using that variability in developing our index. So this is what we come up with. We have two constants that go with our helicity and our convective precip, which is our CAPE-like parameter. And this is how well it does. This is the observations of tornadoes. This is what our index predicts. Now, it's not really a prediction. This is really just a curve fit. This is showing the success of the curve fits, okay? So it looks kind of like that. It's a little bit, it's missing maybe some stuff in the southeast. It's overdoing it down in the Gulf Coast a little bit, where, by the way, there tornadoes could be happening, was it today, or it's being forecast for about now down here in November. But, it has the overall structure right. Nothing west of the Rockies, a big hole here along the Appalachians, and, something along the east, but strongest in the plains. So that's not predicting anything. That's just curve fitting. This is the annual cycle, still curve fitting. So this is the annual number, total number of tornadoes in the index and the observations. You can see it's under shoots in the peak season, which is sort of northern spring, and then and then the index then overshoots in the late season, which is now. But it's okay. And this is showing you that competition. This is what you would get if you only let one of the parameters vary instead of two, holding the other one constant. So this is what you would get just due to convective instability, convective precip, and this is what you would get just due to shear. And you can see that they're out of, almost exactly out of phase with each other. So the actual result is some competition between these two, something like the global warming case, although these changes are much larger. These seasonal changes are much larger. But you put it all together and you get this, which is reasonably successful. Now we want to see what else it tells us. This is going back to that trend. So now this is where we've gone back and now we compute our index. We do the curve fit. We obtain our index, right? We have two constants here. Now you give me any storm relative helicity and convective precip. I can compute for you a probability of tornadoes. So I can go back and compute it just like we did with hurricanes. I can go back and compute it on interannually varying data, keeping the index formula the same. And this is what we get, okay? And this is the observations, which has that big trend in it. And you can see our index has no trend, pretty much. And what that tells you is that the environment for tornadoes does not seem to have been becoming more favorable over time. There's no significant change in it over time, which is another piece of evidence that this observed trend in the actual tornado reports is spurious. And if you go in and adjust this, which is basically detrend it, it's a little more, slightly more complicated than that, but you basically detrend this, and that's this light dash curve. It agrees with our index very well. You can also see that this is for the total annual number every year since 79. You can also see that we capture a lot of the interannual variability. If you look at the up and down wiggles, you see that. Here's April. Here's just for the month of April, the number of tornadoes in April, which is the peak season. A lot of agreement interannually. And this was 2011. I don't know if you remember, there was a very, very extreme tornado year in April 2011. Tremendous devastation in the Midwest and plains. And this is our index. It gives something. Our index was trained up to 2010, and then we calculated 2011. And it gives a value that's extremely high. In other words, this index, given the environment, predicts we should have a lot of tornadoes, which we did. Now, the real number was much higher still. We didn't capture, it didn't get the full magnitude. But it got a number value higher than anything in the training data. In other words, I got it out, makes it out of sample prediction. So that's sort of telling us we do have to keep something non-trivial coming out of this. Last thing I want to say, yeah, that's what I said. Index trained on pre-2011 data predicts April 2011 should be unprecedented, although not as much as it really was. This is now going and looking at that interannual correlations. We have this variability year by year. We can do it for each individual month and compute correlation coefficients. So this is using the NAR data instantaneously to calculate the correlation coefficient between interannually varying number of tornadoes in each month and the actual number. And dark numbers are statistically significant. And you can see there's pretty good, it's not really skill because it's not a prediction, but there's good correlations. This is showing the, let's just stick with this for a minute. Pretty good correlations. It's greatest in the winter. It's pretty good quite good in the summer. It's not so great in the spring. This is doing the same thing in an actual prediction mode. So these are instantaneous. It's not a prediction. In other words, I have to know the environment at the time. This is using actual forecasts from the CFS-V2 model. These are something like, I believe that what these are, if I remember correctly now, they're hindcasts, but they're fair hindcasts, and they're done monthly. So it's like for the next month, starting at the beginning of that month. It's approximately that. So it's like something like a few weeks forecast. And there's still significant correlations in some months. Not exactly in the peak season. It's best in summer. This is showing for June the actual data. This is the number that our index with CFS predicts. This is the number in observations. And it's quite a good correlation. I mean, this is picking the best month, okay, on purpose. But it's quite good. This suggests the possibility of doing forecasts for tornado activity on a longer time scale than is currently done. We have seasonal hurricane forecasts. We don't have them for tornadoes. Tornadoes, we only have the longest severe storm prediction center goes is something like 12 days, and they don't even usually go that far. But they're trying to predict individual outbreaks and with spatial structure. This is just for the whole country. But if you're willing to have a very broad brush, we think there's some hope for tornado activity forecasts on the large scale with some skill out to a month or more. Not, again, no specific specificity about the event, but a little bit of skill, the same kind we have for seasonal hurricane forecasts, which is not much either, but it's enough that people want to look at it. This is just doing this the El Nino thing again. This is now computing our tornado index for El Ninos and La Ninas, and rather than subtracting them, I'm showing them individually. This is El Nino and La Nina, and you basically see that you have fewer in an El Nino and more in a La Nina. These are the observations. So people have done this before with the observations. This is the density of tornadoes. And you see the same thing, but just less statistical significance. These little bullets here, these little circles are telling you where there's statistical significance. And here you don't really have much, whereas here you have a lot. So it's because you're looking at the environment, which has much, this is the environment for tornado formation rather than the actual reports. That's much smoother and better resolved by the observations. So it has a larger sample because you have environment every day where you don't have tornadoes every day. So it gives you just a much robust signal. So this predicted, for example, that we should have had a weak tornado season last year, which we did. And if the current forecast with the current El Nino event holds according to plan, we should have a quiet season again next year, which is a prediction that I'm making now. Just the last thing, this is not my work. This is a paper by Noah Diffenbaugh that did something similar. They took one of these indices, not ours, but one developed by Harold Brooks, and applied it to climate models for CMIP. So they're looking ahead into the future and predicting that in March, April, and May, there should be more tornadoes. That's what this red says. And this is I lost my button here that allows me to get a laser. Oh, yeah. This is a percentage-wise increase in the number of tornadoes with time going forward to 2100. So as I said, CAPE increases, shear decreases, and what they're predicting is that CAPE wins based on this Brooks index. But so this is the state of the art at present. As far as I know, this is the only paper to do this seriously, unless somebody's done it since then and I missed it. But this index is derived from soundings. In other words, what Brooks did is every time there's a tornado, he goes and finds the nearest sounding to it within 6 hours or something, and then constructs his environmental index from looking at that. Whereas but that's really a very different kind of data than climate models. And so our index procedure is has the potential to go a little closer to the climate model itself. And so we want to redo this calculation. We may get the same answer. I'm not saying different valid all are wrong. It's just that it's a tricky problem because you're looking at the small difference of large numbers. The cape's going one way, the shear's going the other way. So exactly how you weight them is going to matter a lot. And we know from the hurricane example that slight differences in how you choose your parameters or what the coefficients are can change the answer, especially in cases like this. So this is sort of future work for us, but we think it's still a problem that needs to be done, looked at more. So that's the end of my material. I'll just summarize to say that although tropical cyclones and tornadoes are totally different physically, there are some similarities in some of the tools that we can use to assess how they're related to climate. And we're starting to get in the regime of high-resolution global models that can handle tropical cyclones, but tornadoes is a long, long time before we see that. So our approach, we're not a big modeling center, and we focus on these quasi-empirical index, which, by the way, they're called, what the hurricane community calls genesis indices is called in the severe convection community in the ingredients approach. If you hear those words, it means the same thing. And I've shown that our indices for both phenomena can capture some amount of natural variability, like ENSO. In the case of the hurricanes, we've done it for the MJO2, although I didn't show that. And we claim, I think our most exciting result for tornadoes is that we claim their forecasts are possible out beyond the 12 days that NOAA currently does. And my colleague Mike Tippett is working with people at SBC to actually try to do that, develop some kind of a quasi-seasonal outlook. In terms of tropical cyclones, I think the thing we've learned from this that's the most interesting so far, as far as the climate change problem at least, is that this model simulated decrease in cyclone number with warming appears related to the saturation deficit, which is something that's been hypothesized earlier, but I think this is the most direct evidence for it that I'm aware of. And although I didn't draw any conclusions about this, I think the global warming influence on tornadoes is delicate due to the Cape and Shear cancellation. So that's future work and something we'll be doing in the future. So that's everything I had, and thank you for listening.
Yeah, just a curiosity. You showed sort of how the granular variability was for the tornado index, but you didn't show it for the Genesis. So have you done similar thing? You showed the comparison between.
I showed the composite. Yeah, we have done it, and it's it has about as much. I mean, it has some amount of skill. Let's see. I mean, I could pull up the paper. It's in that paper somewhere.
Yeah, well,
but it's some amount of skill. It's not. There's a little bit of that is implied by that, but you're asking the question, event by event, how well does it do? And I can't quote you the numbers, but you get some significant correlations. It's not incredible, but the problem is when you go down to individual years, the cyclones, in a way, are even. Well, I don't know if this is true or not. They, the same number of events is even smaller than for tornadoes. They're better observed than tornadoes, but the number of events is small, so there's a sampling issue. But there's definitely, yeah. No, but individual basins. I mean, here and so you're not predicting that number. That actually, there's very little variation in that. You're predicting the much larger variations in the individual basins. There's significant correlations. There's significant correlations. It's not, it's not magic, but.
So you showed that the tornado activity decreases in the El Niño year. What is the main contributor?
Yeah, we haven't studied that in great detail. I don't. What's the physical explanation for that? I mean, I think. I should be able to say that. Which parameter is it? The jet should be south. I mean, it's certainly cooler. So I think it has to be the Cape, but I cannot quote you that No. I mean, yeah. I suspect that it's. I know that John Allen, our postdoc who did this work, will have a satisfying answer for that, and I'm embarrassed that I don't. But I think what happens in El Nino, right, is the jet actually comes a little bit south, and it's cooler and wetter here, at least in winter, and then coming into spring. Of course, it's all tricky from a forecast point of view because this is often when El Nino changes. But so this is, and I forgot to say though that you get decent prediction skill when we do the hindcast thing. You get decent prediction skill if you predict based on DJF ENSO for the next MAM. So we actually think there is there is some actual seasonal skill, not huge skill, but a little. But I'm not giving the physical answer that you wanted, and yeah, I think it has to just be that it's cooler. But that's the best I can do, I'm afraid.
I think I don't remember if it's Bell or if it's Harold, but in some of the recent work, there was an argument made that the days that had increased CAPE, the vertical shear decrease isn't as bad
Right.
as in days when there's already low CAPE. So in other words, you're losing your strong vertical shear on days where the CAPE wasn't high to begin with. So is that something that you'd be able to...
In the global warming problem?
Yes.
Yeah, and I think that was Brooks's basically critique of Diffenbaugh. Yeah, that's interesting. So is that something we could test? And the answer is yes, but not with our current index, because similar, what we're doing differently from Diffenbaugh is we're training our index on large-scale data sets rather than proximity soundings. But what we're doing the same is we're taking the climatology. So to do that, what you have to do is you have to use some measure of the jointness on a daily time scale. But you can do that if you have daily data. So if you have daily data, then you have to make you could do something. You could do it just from daily data, or if you want to do it for monthly data, that comes from you could take the product of CAPE and shear, or however you want to make it up, compute it daily, and then average that over the month.
But you also need to assume that those parameters are independent.
Well, but I can make a parameter that captures the dependence and then make that independent of it. You see what I mean? In other words, it's like this. It's like we're doing, CAPE and shear, and we can do instead, we can do instead CAPE prime S shear prime bar, or something on the daily time scale. So we would have to deal with that. We would have to we have to make a parameter that captures that covariation. With our current index, no, we wouldn't get that. And he, Harold could be right.
Yes, so the way I understood it correctly, so that the index for tornado genesis was obtained by fitting all the monthly data after just 1979.
Well, it's monthly. It's the climatological annual cycle.
Yes, so each month but since 1979.
We take all the data since '79, but the reason I'm rephrasing your question, I just want to make sure it's clear that we're not using it year by year. We take all the Januaries averaged together, but yes, since '79.
Yes, so but then when the index was obtained from that data, but when you hindcast it, you don't get the same trend.
Well, but again, that's because we don't include the trend when we train it. So see what I'm saying? What I'm training it on is 12 maps like this, each of which is all the data average. So our training procedure doesn't know the difference between '79 and 2012. They're all the same. They're all.
But the CAPE and the other quantities are different. I mean, the predictor.
Yes. So right. So then that's what we do to derive the index. Yeah. That gives us our function and our parameters. Then I go and compute it each year from the data, and then there is no trend. You're right. That's my point exactly. That's why we don't believe this. It's one of the reasons why we don't believe it. I mean, the first reason we don't believe it is that the tornado guys tell us we shouldn't believe it because because the practices have changed over time and there's more storm chasers, and anybody in Oklahoma will tell you don't believe this. But this is just consistent with that because the environment doesn't show the trend. Does that answer your question, or? not.
For sure, no, thank you.
Yeah.
So
Yes,
if I
sir.
take you back to the diagram when Edmund asked the question, El Nino minus
The composites for El Nino?
Yes.
Of the cyclones or the?
Of the hurricanes, I think.
Yeah. Somewhere up here. Yeah, that one?
That one. So the lower part, which you want to relate to the index, is
Yep.
the observed track density, not the observed track density of the El Nino minus La Nina.
No, it is the El Nino minus La Nina. Sorry. Both of them are El Nino minus La Nina. But this is index, this is observed.
Okay. So the second part is, don't you think by doing El Nino minus La Nina, you are over amplifying the signal as opposed to El Nino minus the normal year?
Well, you can do it either way. I mean, the point is, yes, we wanted to make the signal as big as we could to see it, but I think it's fair as long as you compare to the same quantity from the observations, right? I mean, if I do El Nino minus neutral, I would claim that I would get something that looks similar, but the amplitude would be lower, and similar here. So you're quite right. We're making the signal as big as we can make it on purpose, but we're comparing what I think is a fair way to the observations by treating the data in the same, as close to the same way as we reasonably can, given that these are smooth fields and these are kind of sparse points. But
yeah, my fear was that it would distort the sea surface temperature signal, which drives your I'm not very good with the atmospheric part, but that's the heat engine, which
yeah,
and
but
that was the parameter you used for getting the
right.
the generation of the
But what's the distortion? I don't.
because it's like taking the extremes, and I think that's a particular case than a general case.
Well, right. There's many things you could try to predict, right? It's not predict is not quite the right word because these are not forecasts, but predict in the sense of explain. Many things you could try to explain, and we chose to plot the difference between El Nino minus La Nina because that's the most compact way to give you the ENSO signal in one map. But so you could do it many other ways, and the signals might be smaller. But I think this isn't the only. There's many ways you could test a method like this, but I still don't see anything unfair about it, since we're just asking the same question of the observation. There's many other features of observations I could try to explain. But this is the grossest. If we couldn't do this, let's put it like this way. If we couldn't do this, we would be in trouble. So then you could ask, well, maybe there's other things that you still fail at, and that could be true. But yeah.
Well,